Welcome everybody to the very first differential calculus video that I'm going to be releasing, and today what I'm going to be discussing is going to be a quick introduction to the concept of a limit. But before it is that I get into that, I want to discuss two of the main fundamental problems that we're going to be addressing in calculus as a whole. And the two main problems that we're going to be trying to solve in calculus, specifically calculus 1, this is going to be the main focus for the next few videos that I'm going to be releasing, is going to be calculating the slope of a curve at any given point P. And up until now we know how to calculate the slope. It's going to be the change in y over the change in x. For those of you that know, it's normally formalized as the change in y over the change in x, otherwise known as y final minus y initial over x final minus x initial. But the only problem with this model over here is it only works for a linear curve. So what we're going to be doing is we're going to be modifying it a little bit in order to calculate the slope of a curve at any given point on any kind of curve, no matter what it is, whether it's exponential, logarithmic, polynomial, any kind of curve you want, you can calculate the slope at any given point on that curve using the concepts that are going to be taught in calculus. Next up, we're going to have the idea behind calculus 2, which is called integral calculus, and that's going to be taking the area under a curve between two given points. So imagine we have this function right over here and we choose 2 points A and B. We want to calculate the exact area under that curve. We don't want any approximations. We want it to be a perfect, I don't even want to say approximation anymore. We want a perfect area for what is between points A and B under that curve. So without further ado, introduction to limits, let's get going. And the first thing that I'm going to be bringing up right over here is going to be a graph that I had just erased not too long ago. And it's going to be this point P. We want to calculate the slope at this given point P, but we don't know how to do so just yet. We know that up until now, I discussed it not too long ago, it's going to be the change in y over the change in x. But what we want to do is we want to take two given points, 2 points that are going to be so close to this point P that are going to replicate the slope. Basically what happens over here is we're going to have 2 points, say A and B, and we want an approximation for this slope over here. If we tried to connect these 2 points and use our regular formula where it's going to be delta y over delta x, this would be an approximation for this slope. Not a very good approximation, but still an approximation nonetheless. So what we want to do in order to get closer and closer to the real value of whatever it is that this slope is we want to bring the points closer and closer together until they're infinitely close to the point where there's no difference between them. So what we're going to do is we're going to bring the points over here. This marker doesn't want to work. And we're going to calculate this slope over here. This is a better approximation of the slope at point P, but still not very precise. So we want to bring the points closer and closer and closer together until they're pretty much on the same point. And this idea of getting closer and closer and closer to something and without ever actually touching it is the concept of a limit. And where's my eraser? This is formally written down as the limit as x approaches a certain value. Let's say that that certain value is called a, of f of x, which is going to be the function that you're going to be plugging it into, is going to be L. L is going to be the value of the limit that you're going to be evaluating. So what I want you guys to do right now is consider the following function that I'm going to put up right over here. Imagine f of x is going to be equal to x squared plus 2x plus 1. This is a quadratic function, and what we're going to be doing with this function is evaluating the limit as x approaches 2. What we want to do is we want to use values that are infinitely close to, but they never actually touch 2. So this can be written down as the limit as x approaches 2 for x squared plus 2x plus 1. So what we're going to do now is we're going to draw out a table of values which is going to tell us our x input and our f of x output, otherwise known as, this can be equivalent to y if you'd like. So if we were to try to plug in 0 into this function right over here, 0 plus 1, so our x is going to be equal to 0 and our output is going to be 1. Sorry about that, phone was ringing, and anyway, let's continue from where it is that we left off. So imagine we want to take values that are closer and closer to 2 but never actually touch 2. This is going to be the concept of a limit that we're trying to explore right now. So right now, if we were to plug in the value 1 into this function, 1 squared plus 2 plus 1 is going to be equal to an f of x output of 4. Say we want to get even closer to 2. What we're going to plug in is we're going to plug in 1.9. Take the value 1.9, plug it into this function. This is not something that I can do in my head, but our f of x output in this case is going to be 8.41. Now imagine we get even closer to 2. We're going to plug in 1.99. The output that we're going to get from this function is going to be equal to 8.9401. 9401. Now we want to get even closer and closer to 2, so we're going to plug in 1.999. And this is basically the idea of a limit. You're getting closer and closer and closer to that point, but you're never actually touching it. This is the overall idea, the overarching idea of limits. So what we're going to plug in is 1.999. Our output is going to be 8.994001. 8.994001. Now let's take things from the other side. So up until now we had values that we plugged in that they were on the left side of 2. So on the left side of the number line. So you have 0, 1, 1.9, 1.999. Now we're going to take values on the right side of 2. That means that we're going to have values such as 4, 3, and 2.1, 2.01, and you're getting closer and closer to 2, but we're never actually going to touch 2. Essentially, we're going to plug in our x and our f of x, otherwise known as our y output. Our x is going to be, say, 4, so we're going to plug 4 into this function over here. 4 squared is 16 plus 8, that's going to be 24. This is going to be equal to 25. That's going to be our output. Now say we want to get even closer to 2, we want to plug in 3. So we plug in 3, 3 squared is 9, plus 6 is 15, plus 6, plus 1 is going to be equal to 16. So our output over here is going to be 16 if we were to plug in 3. Now imagine we're getting closer and closer to 2. We're going to plug in 2.1. Our input is 2.1 and our output is going to be 9.61. Get even closer to 2, 2.01. Our output is going to be 9.0601. 0601. And finally, we're going to plug in 2.001. And our output is going to be 9.00601. Let me see. 9 points. Perfect. And there's going to be a general trend when it comes to plugging these values into a table of values such as this. You notice that the closer we get to 2, the closer our output value is getting 2 but never approaching 9. So we plug in 0, we get 1, we plug in 1, we get 4, we plug in 1.9, we get 8.41. This is already pretty close to 9 as it is. We plug in 1.99, we get to 8.9401. And there's always going to be a value that's going to be a little bit closer to 2, but not at 2. Take 2 points and try to find a space in between them. Try to find a value between 1.999 and 2. You'll be able to. There's always going to be a value that's smaller and in between them. This is the concept of a limit. So here, imagine we plugged in 1.9999999. It's going to be something that's infinitely close to, but not touching the value 9. So in this case, what we're going to be doing is coming to the conclusion that the limit as x approaches 2 for this function right over here, the limit as x approaches 2 for, say, f of x is equal to 9. And evaluating limits of polynomials is actually pretty easy because all you really need to do in order to evaluate the limit is you need to plug in the value. Plug in the value that you're going to be evaluating the limit of, and that's going to give you the limit. You don't need to draw any complicated table of values or anything such as this. The only time evaluating limits gets a little more complicated is when you have fractions where it is that they're in the form of 0 over 0, infinity over infinity, and these are called indeterminate forms. This is exactly what the first bit of a Calculus 1 class is going to focus on, evaluating complex limits where it is that you're trying to manipulate the functions in whatever way possible in order to get rid of that indeterminate form. So say something appeared and it gave you a output of 0 over 0. You cannot divide by 0, the universe explodes otherwise. So what you need to do is you need to manipulate the function in order to make it so that this 0 over 0 disappears. So without further ado, let's get on with one of those problems. I'm going to erase all this. You may notice a limit of f. Oh yes, just something that I wanted to note down. I already said it earlier, but let me note it down just because I can. The limit as x approaches a is going to be equal to the limit as x approaches a for a function of x is going to be equal to f of that a. So imagine we had the limit as x approaches 2 for a certain function, whatever that function may be. The limit for that function is going to be f of 2. Plug in 2 into that function, there's your limit. Easy as that. And limits become slightly more complex. Indeterminate forms, already went over this. And for example, we want to evaluate the following limit. Let's just erase this right over here. Leave that up there for now. Let's take the limit as x approaches 1 for x squared. What is this? No. This is going to be the limit as x approaches 1 for x minus 1 over x squared minus 1. Now we can't use the same strategy that I discussed earlier where it is that we plug in the value, because essentially what happens is we're going to have an output of 0 over 0. We plug in 1 over here, we're going to get 1 minus 1, which is equal to 0, and 1 squared minus 1, which is also equal to 0. That is called an indeterminate form, equal to 0 over 0. And there's a much easier way of evaluating indeterminate forms. We're going to be discussing that later on in the course using the concept of a derivative, which is really cool. I love this concept, but for now we're going to be breaking it down the old-fashioned way. This is probably what your teachers are going to want you to do on the first test in terms of evaluating limits. There's no cheating in your first tests. So the first thing that we're going to be doing is we're going to be learning, we know that this function right over here, this denominator, can be factored out. So let's rewrite this function over here. Limit as x approaches 1 for x minus 1, and this can be split into two different functions. Product of two functions, which is going to be x plus 1 and x minus 1. Now we have a common factor in both the numerator and the denominator, which can be crossed out. So we cross out these, they cancel each other out. All we've got left is the limit as x approaches 1 for 1 over x plus 1. And now it really is as simple as plug and chug. All you need to do is you plug in number 1 into this function. So f of 1 is going to be equal to 1 over, you plug in 1 over here where you see the x. F of 1 is equal to 1 over 1 plus 1, which is equal to 1/2. So the limit as x approaches 1 for x minus 1 over x squared minus 1 is equal to 1/2. Now the main idea that you need to keep in mind whenever it is that you're evaluating limits is you need to algebraically manipulate it however it is that you can until it is that you can plug in the value that it's asking you to plug in, and it's not going to break the function. If you try dividing, if the output of the function is a division of 0, then you haven't algebraically manipulated it well enough in order for it to work. Sometimes we're going to come across these ideas of limits that do not exist. We're not going to discuss those in this video. For now, I'm going to put up another one. And keep in mind that your teachers may actually try to trick you by giving these functions that don't need to be algebraically manipulated in order to evaluate the limit. So here's a pretty good example of one of those functions. So let's say we want to take the limit as x approaches 1 for 3x squared plus 5x plus 1 all over 7x squared plus 2x. And this looks pretty scary for somebody that's never really done anything concerning limits up until now, but there's no manipulation that's actually necessary for this problem over here, because say you wanted to plug in the value 1 into this function. Into the numerator we plug in 1. F of 1 is going to be equal to 3x squared is going to be 1 plus 5. 3 plus 5 plus 1 is going to be equal to 9. And then in the denominator, 1 squared is going to be equal to 1 times 7 is equal to 7 plus 2 is going to be equal to 9. So f of 1 is going to be equal to 9 over 9. As you may have noticed, that's not an indeterminate form. This is not equal to 0 over 0, so it's fair game. You are allowed to do this. So 9 over 9 is equal to 1. So the limit as x approaches 1 for this big nasty function over here is 1. So the last problem that I'm going to be evaluating in this introduction to limits is going to be something a little different. It's going to require a little more algebraic manipulation than anything that we've seen up until now. And that's going to be the limit as x approaches 0 for the square root of x squared plus 9 minus 3 over x squared. And one of the things that you really want to do with all of these functions is you always want to plug in the value first to see if it requires any algebraic manipulation, because sometimes the teachers really do like to screw with you, just like in the problem that I had just given you previously, where all you had to do was plug in the value, limits evaluated, done. But in a problem like this, let's try plugging in 0. If we were to try plugging in 0 into this function over here, we would get 0 plus 9, the square root of 9 is going to be equal to 3, so 3 minus 3 is equal to 0 in the numerator, and then you got 0 in the denominator. So yes, this does equal to 0 over 0. So this is called an indeterminate form. This is where it is that we need to algebraically manipulate the problem a little bit before it is that we can carry on. So what we want to do for this problem is, let's rewrite this as the limit as x approaches 0 for square root x squared plus 9 minus 3 over x squared. And what we want to do is we want to multiply by the value 1. Or we want to multiply by 1 in a very special way. So what we're going to be doing is we're going to be multiplying by the conjugate of the numerator over here. And the conjugate is basically, see this minus sign over here, you're going to be multiplying by this entire expression, but instead of the minus sign, it's going to be a plus. That's the idea of a conjugate. So we're going to multiply by x squared plus 9 plus 3, and then in the denominator the exact same thing. So it's going to be square root of x squared plus 9 plus 3. Would you agree? Of course you would agree. Would you agree that this value is equal to 1? Yes? Alright, we're going to move on like this. So say we wanted to multiply this out, limit as x approaches 0. As x approaches 0, for this is going to be distributed, so it's going to be x squared plus 9 minus 9. The 9's over here cancel each other out. And then here you're going to be distributing this, so it's going to be x squared multiplied by the square root of x squared plus 9 plus 3. So we're going to rewrite this, make it a little bit cleaner, clean it up. Limit as x approaches 0 for x squared over x squared times the square root of x squared plus 9 plus 3, all in brackets. We didn't distribute this. And we notice that we have a common factor of x squared among these two functions over here, the numerator and the denominator, so these cancel each other out. So here we can rewrite this as the limit as x approaches 0 for 1 over the square root of x squared plus 9 plus 3. Now, If we tried to plug in 0 in this function, we have no problems anymore. If we tried plugging in 0, we would get 1 over, we plug in 0 in for x squared 0 plus 9 is going to be equal to the square root of 0 plus 9 is going to be equal to 3 plus 3, so the entire limit is going to go to 1/6. The limit as x approaches 0 for this nasty function right over here is equal to 1/6.